All right, good morning. We're going to go over sections 4.2, linear and quadratic functions. And so we're going to make some definitions. Some of this we've seen before already, and we're going to talk about a few details about these particular kinds of functions. All right, so for a linear function, I think it's something that's very familiar to us already. It looks like a line, right? So we spent a good bit of time graphing lines, y equals mx plus b, and all that kind of stuff. And that's actually how we can define a linear function. We can just say it's of the form f of x equals ax plus b. And here we specify a is not 0. Well, actually we could even let a be 0 as well. But if a is 0, then we have a constant function, which is actually a straight line as well. It's a horizontal function. Okay, so we'll mention that if a is 0, f of x equals just a constant b, which graphs like a horizontal line. And we saw that. If you remember, how do you define the equation of a horizontal line? Y equals a constant, right? And so that's what we're saying here. Okay, now the graphs on these are not very special to us. I mean, we've already dealt with this a lot. So you could have something like this. Let me see. This is just example 1 from the text. We want to graph, let me pick one, f of x equals 3x plus 2. Now, we're kind of new to functions, so one way we could think of this is like a table of, remember we talked about inputs and outputs, and that's the best way to think about functions, is you're plugging in something, you're putting in a coin, and you're getting something out of it. Okay, so for example, I might plug in 0, and if I plug in 0, my function value becomes 2. If I plug in -1, for example, I get 3, so that's 3 times -1 plus 2 is -1. If I plug in 5, for example, I might have 3 times 5 plus 2, which is 17. Okay, and what I'm doing here is creating a list of ordered pairs. Now, we know how to graph a line, right? We've done that before. So if I have my axis like this, the line 3x plus 2 has a y-intercept at 2 and a slope of 3. So that means for the next point, I just need to go, remember slope is rise over run. So I'm going to go up 1, 2, 3, and over 1. There's my second point. And now just carefully try to connect these 2 points in a straight line. And there's my line. There's f of x equals 3x plus 2. And if you notice, the things we got from our table, like 0, 2, is sitting here on the line. Here, let's see, -1, -1 would be down here somewhere. Right? And if I did 5 and 17, that's kind of up here somewhere like that. And we could have picked different points, and we just keep going along that line, that way. All right, I hope that makes sense. Nothing really new to us. There's nothing more we can really do. We could just, we mentioned the constant function. So let's say if we had a part b here, how about f of x equals 5? All right, well, I know what that looks like. Y equals 5 is just a horizontal line. So just come over here at 5 and just go straight across. That is the constant function 5. And if you wanted to think about the table, what would a table look like if we're doing it that way? You could say here's f and here's f of x, and whatever I plug in for x, I get 5 for my output, right? Because it doesn't matter what coin I put in this machine, you're always going to get 5. Okay, so this is kind of like the, a few years ago at Halloween, Reese's set up a machine where you could dump in your Halloween candy and it would give you Reese's for your Halloween candy. Whatever you plug in, you get the same thing out, okay? All right, now we're not going to spend a long time on linear functions because they're not very interesting, and we've already covered them a good bit when we talked about graphing lines and things. What we really want to look at is quadratic functions. And quadratic functions are the form where, well, we have a squared term. And we've dealt with quadratic equations a lot already, so we know this a little bit. Okay, so we say it's of the form ax squared plus bx plus c. And here we need f of x equals that. And this time we really do need a to not be 0, because if a is 0, the thing's not quadratic anymore. It's going to be linear or constant. Okay. Now the question is, what do these things look like? So I'm going to try to use some Desmos here to figure that out. Let me get an example of one, and then we'll look at it in Desmos. So for example, let's graph, we'll say g of x equals, let's just do x squared, okay? And actually, before we graph it, why don't we try to figure out through a table kind of what these points look like. So again, I'm plugging in x, my outcome, or my output is whatever I get when I plug x into g. So for example, if we pick 0 for x, then my output is 0 squared, which is 0. So that gives me 1 point on the graph, 0, 0. I hope that makes sense. Okay, so if I plug in 1 for x, my output's going to be 1 squared. 1 squared is 1, so I get the point 1, 1. All right, let's do 2. How about if I plug in 2, 2 squared is 4. So now I have the point 2, 4. And here's a weird thing. If I plug in -1 and -2, respectively, I get -1 squared, which is 1. So I have the point -1, 1. And then I have -2 squared, which is 4. So I get -2, 4. All right, so this thing's not going to be aligned, because if you notice, my outputs, as I'm going up, the outputs are going up. But as I go in the negative direction, the outputs are going to reflect that as well. Okay, so what does the graph of this look like? All right, so let's transition to Desmos, and I will show you. Just give me a second. All right, here we are. This is Desmos.com, and it's a free service. You can create an account or just come on and start graphing. All right, and so what I'm going to do is I'm going to graph the points we had. So we picked 0, 0, and if you notice on my graph, it shows up. All right, now I can keep graphing points just by putting commas in between them. So we had 1, 1, and we had 2, 4. And then we went in the negative direction. I had -1, 1, and -2, 4. We could pick some others. Let's see. If I had, it was x squared, right? So if I put 3 in, I get 3 squared, which is 9. Where is that on my graph? That's up there. Okay, so notice I get this weird shape if I just type in g of x equals x squared. There it is. There's my graph. And in general, quadratic functions are going to graph like this shape. And this shape is called a parabola. Okay, now I'm going to show you a few things here. One, this 0, 0, 0 here was the kind of the point of this parabola. We call that point a vertex. Also, if you notice, if I let x be 0, just the line, I have, if you see, can you see this green line here? Okay, that green line kind of it chops the parabola in half in reflective pieces, right? So if I take the positive side and fold it over on the negative side, I get the same shape on both sides. So this line right here through the vertex is called my axis of symmetry. All right, now let's come back to our notes. Let's write some of this down, and then what we want to do is figure out if I'm given a quadratic equation, or a quadratic function, can I find the vertex and can I find the axis of symmetry? That's what we want to do. All right, just bear with me a second. All right, here we are. So let's look at our parabola again, and I'm going to pick just a generic parabola. I don't want the same one because I want to point out something. So let's suppose we had just some parabola out here like this. All right, we got some key elements to this thing. So first we have the vertex. And typically we denote the vertex with the letters H, K. H for the x coordinate, K for its y coordinate. Okay, we also have that we have this axis that kind of chops the parabola in half. Now mine's not scaled. The Desmos graph was much better than mine. But we call this the axis of symmetry. And I think you can kind of see why, right? I mean, that's the thing that's kind of folding this thing over on itself. If we folded it about that line, we'd see that on both sides of this axis it's exactly the same, even though clearly in my picture it's not. And the axis of symmetry is a vertical line that passes through the vertex. So it's going to have this x coordinate. And how do we designate a vertical line? We do that by saying x equals h, right? So I think that makes sense to us. Okay, so let me get an example. And we're going to try to sketch a graph of this thing, trying to find its axis of symmetry and its vertex. And there's one other thing I want to do. So what would happen, let's go back to Desmos for a second. Let's look at some different parabolas. All right. So we have g of x equals x squared. Now let me do this one. Let's see. Let's let h of x be, how about 3x squared? So I multiplied it by 3, and I got this purple graph. And it's still a parabola, but notice it's kind of shrunk or condensed. If I'd said, let's let k of x be, I don't know, how about 1/2 x squared? Then I get the parabola again, but this time it's widened out. Okay, so it looks like if I multiply the coefficient in front of the parabola, it kind of either condenses it or stretches it out. And if we're playing around with this, let's let f of x be, how about 1/10 x squared? What do you expect? I would expect it to be a parabola, obviously, but I think it's going to be stretched out even further. Yeah, look at that. So it looks like as a gets closer to 0, a being the leading coefficient, gets closer to 0, it kind of stretches out. But if I let a be large, let's do one more. Let's see, I did f, g, h, k. How about j of x? Let's pick something large. How about 15 x squared? I think this is going to be really thin. Yep, see that? So as a gets larger, my parabolas kind of get thinner and thinner. What would happen if it's negative? Let's do an I of x. So if I did a negative x squared, that makes sense. It flips everything upside down. That would make sense, right? Because you think your points, I mean, 0, 0 still works. But if I said 1, and then I plug in 1 into I, that's negative x squared. So that'd be negative 1 squared. Be careful with your parentheses. That's negative parentheses 1 squared. I get negative 1. And see, that points on the parabola. And I could do the same thing with 2, negative 4, and so on. All right, so the negative a flips my graph upside down. Okay, so let's try to summarize this as well. Let me go back to my notes. Just bear with me. All right, so let's see. If what did we say? If a is negative, the graph Well, let's go ahead and say the parabola. It's upside down from my standard parabola. We could say, why don't we say it this way? The standard parabola opens upward, it opens downward. Okay, so in other words, it looks something like this. Okay, now if the absolute value of a is less than 1, so obviously absolute value is between 0 and 1. I mean, it's greater than 0, right? And the reason I say absolute value is because this will work too if it's flipped upside down or not. But if the absolute value of a is between 0 and 1, the parabola is, what do we say? Like when we did 1/10, remember it was wide? We'll say wider than x squared. And if the absolute value of a is greater than 1, like when we said 15x squared, what happened? It kind of shrunk down like this. The parabola is thinner than x squared. All right. So these are kind of our rules for parabolas. What do we have? We have an axis of symmetry, a vertex, and then we see the leading coefficient has these properties that help us kind of figure out how the graph goes. So why don't we do all this together and try to graph. Here's my example. Example 2. I want to sketch a graph of, what do I have here? F of x equals negative x squared minus 2x plus 3. Negative x squared minus 2x plus 3. Okay, now when we're sketching the graph, what would be helpful is we need the vertex and the axis of symmetry and all that stuff, but what is also helpful is if we have the x-intercepts. Okay, now let me go ahead and tell you, we're going to pause this for a second. In the parabola, I mean, there is a way to write the parabola, the function of the parabola. What am I trying to say? There is a way to write f of x here, my quadratic function, such that it's obvious what the vertex is. And we call this vertex form. And vertex form looks like this. If you can get f of x to be a x minus h quantity squared plus k, the vertex then will easily be found as the point hk. All right, so if we can get our f of x from example 2 to look like that, I'll know the vertex, and I'll also know the axis of symmetry, right? Because the axis of symmetry just passes through the x-coordinate, so that's going to be x equals h. I know those two things. How do I do that? Okay, now let's get back into our question, and we're not going to do that yet. Okay, so there's two parts to this. The first part is we want to find the intercepts. If you want to find the intercepts, you're better off leaving the function not in vertex form, because to find the x-intercepts, what do? So for the x-intercepts, if you remember, that means this is where it crosses the x-axis, which means your height is 0. So in other words, your y-coordinate is 0. We're going to let y be 0, or in functional notation, we're going to let f of x be 0. And now I'm trying to solve a quadratic equation. All right, and we've spent some time doing that. We know how to do that. So for this quadratic equation, I need to try to factor. What would be easy is if I multiplied both sides of my equation by -1. 0 times -1 is 0. And then the rest of my equation becomes x squared plus 2x minus 3. For some reason, having a positive leading coefficient makes it easy to factor, makes it easier. And now I got to think of two things, and multiply give me -3, add give me +2. How about +3 and -1? Does that work? I believe it does. X squared plus 3x minus 3. That's right. And so I get x equals -3 and +1. Those are my two x-intercepts. okay? The y-intercept, if you want the y-intercept, how do you get the y-intercept? You let x be 0. So in other words, I'm just going to find f of 0 here. And again, my function is this negative x squared minus 2x plus 3. So that's negative 0 squared minus 2 times 0 plus 3, which just equals 3. So there is my y-intercept. All right, so we have done the first part, finding the intercepts. The second part is you want to find your vertex. Okay, so here we need to get it now in vertex form. All right, so now we need to find the vertex. And the trick is convert to vertex form. And how do we do that? That's a good question. All right, so let's start off with what our function is. Our function is negative x squared minus 2x plus 3. And I need it to look like, remember vertex form looks like this. A times x minus h quantity squared plus k. That's what I need. That's what I need. Okay, so how can we do this? Well, the first thing you want to do is you want to put parentheses around, actually let me write it again. You want to put parentheses around your linear and your quadratic term. I'm putting parentheses around my linear and my quadratic term. Let me make a note of that. I'll say group ax squared plus bx. Okay, so like that. The second thing you want to do is you want to take out the anything, well, let me say it. You want to make the leading coefficient of this group 1. All right, so right now it's negative 1. So I'm going to factor out the negative. So I have x squared plus 2x on the inside now, right? And then I have plus 3. So what I did there was make the leading coefficient 1. All right, so I want to make the leading coefficient 1. Now, the reason I'm doing this is, look, this now looks closer, it looks closer to the form I need, to the vertex form, right? I mean, I have this group thing plus a 3 out there, but notice in the vertex form, I have x minus h quantity squared, so I have a perfect square. Is there a way I can make x squared plus 2x factor as a perfect square? Yes. We've seen this several times now. We saw it with circles. We saw it with quadratic equations. What we can do is complete the square. All right, and that's exactly what we're going to do. So it looks like this now. I'm going to say negative. We have our x squared plus 2x plus fill in the blank. And what we did last time with completing squares, we said we're going to add that to both sides of my equation. I can't do that now because I'm in functional notation. So what I'm going to do is add it in, and then immediately subtract it, like that. Because whatever that missing piece is, when you add it and subtract it, that's 0, right? So I didn't change anything. And what I have to do is figure out how to fill in what's missing. And we do that by, again, completing the square. Okay, so if you remember how to do that, you take your linear term, so here that's the 2. I divide by 2, so I say 2 over 2 equals 1. And then I square that, so 1 squared is 1. And then I add that back in. So that is the missing piece. It's 1, but I'm not just adding in 1. I'm going to add 1 and then subtract 1. So I say plus 1 minus 1, like that. Now, let me show you why that works, okay? So first of all, if I just had x squared plus 2x plus 1, that would factor very nicely. That would factor as x plus 1 quantity squared. So all I need to do is figure out how to get rid of this negative 1 here. Well, all I have to do then is take the negative 1 out. All right, so I can do that. So let's see, we now have negative x squared plus 2x plus 1. That's good, because that's going to factor very nicely. And then I need to take out this negative 1. But remember, anything inside the parentheses is being multiplied by what's out front, right? So anything here is being multiplied by this negative in front. So this is not really a negative 1. This is a negative 1 times negative 1. This is positive 1, right? So I'll write it like this. Negative 1 times negative 1, right? Because don't forget, this negative out front means negative 1 times everything inside. So when I took it out, it's like I had to apply the taxes to it. The taxes was multiplying it by negative 1. And then I have the plus 3. Okay, so now finally I can factor. Let's see, I get negative x plus 1 quantity squared. And then when I add the positive 1 and the 3, I get plus 4. Look, it's now in vertex form. Okay, now it feels like a lot. It's really not though. Let me run through it again real quick. All I did was group my quadratic and linear terms together. That's what I did here. I took out my leading coefficient, which is what I did there. And then I completed the square, something we've already done a couple times when I did there. And the only thing different was instead of adding it to both sides of my equation, which I can't do because it's not really an equation, this is just the definition of what f of x is, I had to add it and then immediately subtract it. Now in order to factor the way I want, I had to take out that negative 1 that was being multiplied by negative 1, right? Because everything in the parentheses is being multiplied by negative 1. And then finally I have it in vertex form. Okay? All right, now from there, what is my vertex then? So remember, if I have it in vertex form, which is a times x minus h quantity squared plus k, the vertex is hk. So h in this case is not 1, but negative 1. And then my k is 4. There's my vertex, a negative 1, 4. We are ready to graph this parabola with the information we have. Okay, I hope this makes sense. All right, so let's take a look. We said our intercepts were what? Negative 3 and 1 for the x-intercepts, and 3 for the y-intercept. Okay, so when I come down here to graph, I said what? Negative 3 and 1 for my x-intercepts. There and there. That's negative 3 and 1. We said positive 3 for my y-intercept. And we said the vertex was at this point negative 1, 4. So that's up here. That's the point negative 1, 4. That's the vertex. And now we'll try to carefully plug in all the dots. It kind of goes like this. It kind of goes up. It hits that vertex, goes back down, and you have something kind of nice like that. This is the graph, 1 quantity squared plus 4. Notice here, my a is negative 1, so it makes sense that it's going to open down, and it's going to be just as wide as x squared. All right, now let's verify our work here on Desmos, just to make sure it looks the same. I'm pretty convinced it's going to be, except the Desmos one's going to be a little nicer looking because it's more exact. All right, so let's clear off some of this stuff. We have a lot of functions here. And our function was f of x equals negative x plus 1 quantity squared plus 4. And this black graph is our graph. Now notice, let me highlight, we said that we had x-intercepts at negative 3, so it's negative 3, 0, comma 1, 0. That was our x-intercepts. We had a y-intercept at 3, so that'd be 0, comma 3. And we had a vertex at negative 1, comma 4. And look at those red dots. Can you see them? There's my intercept, 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 vertex. We got it. We nailed this thing. All right, I hope that makes sense. Now, I'll show you one other thing you can do. But I don't typically like to do this, but there's another way to find the vertex. If you have f of x equals ax squared plus bx plus c. So if you don't want to complete the square and you still want to find the vertex, you can do that. The vertex is going to be like this. Negative b over 2a, that's your x-coordinate. Your y-coordinate is f of negative b over 2a. So you take the x-coordinate, plug it in to get your y-coordinate, which makes sense. And if you actually did the algebra on that, what that would make your y-coordinate to be, you have negative b over 2a for your x-coordinate. You get 4ac minus b squared all over 4a. That would be your y-coordinate. I don't like doing this because why memorize all this when we can just hash it out ourselves with the algebra? The algebra is stronger than we realize. Okay, let's try one more. Let's try one more. And I'm not gonna do this. I'm gonna do the completing the square again. I don't want to make sure we feel good about it. All right, so this is example 3. Let's just find the vertex. We won't worry about the graphing. Let's just find the vertex of x squared minus, so we have, f of x equals x squared minus 4x plus 8, like that. Okay, x squared minus 4x plus 8. So here, again, I'm going to try to complete the square. So I'm going to say f of x equals x squared minus 4x plus 8. But remember, I'm going to group the squared and linear term together. The leading coefficient is 1, so I don't really have to do anything there. What I need to do, though, is complete the square. So I'm going to say I have x squared minus 4x plus something minus something and then plus 8. Let me put in my parentheses again. And I like just mixing up the colors, so just bear with me on that. All right, now the negative 4, I come over here and I say that's negative 4 divided by 2, which is negative 2. And then negative 2 squared, which is positive 4. And that's the magic number that I need to add in and then subtract. Okay, so I've completed the square now. All right, now the next thing I have to do is I need to move the negative 4 out, which means I have to multiply it by whatever my value of a is. Here a is 1, so it makes it a little easier on us. I have then x squared minus 4x plus 4 minus 4 plus 8, like that. I just took out the negative 4. And finally now I can write it in vertex form. And how is that? X squared minus 4x plus 4 is going to factor as x minus 2 quantity squared. And then the negative 4 plus 8 just becomes plus 4. So my vertex of this graph is 2, 4. There it is. And I hope this makes sense. All right, now let me show you an example where quadratic functions come into play. They're actually pretty useful. And one way they're useful is, remember, area is length times width. So if area of a rectangle is length times width. So if you have a rectangle where you don't know both sides, you're going to get an x times an x, which is quadratic. Okay, so let me show you here. So we have a farmer plans to use 100 feet of fencing to make a rectangular garden alongside the barn. Okay, so let's get a picture of that real quick. Here's my big red barn. Here's my barn. And he wants to build a rectangular fence like this. Okay, and he's only got 100 feet of fence. All right, now how should he split up the fence along the three sides in order to maximize his area? Ooh, okay, so let me write that down. The farmer wants to, I'll write it this way, make a field of largest area. And that's kind of an interesting question. I mean, should he make, maybe he should make it like long and skinny like this. Would that maximize his area? Maybe he should make it kind of flat and long. And I mean, I drew this here. Maybe that's too much fence. Maybe he doesn't have enough fence for that. Or should he do some sort of average in between? Which one of these fields has the most area? And we're not just trying to guess. We're going to figure out exactly how much it is. All right, so here's how we're going to do it. Let me erase some of these fields. It's too much going on. And let's draw a nice field here. And let's label one of these sides as x. Okay? If that's x, I don't know the other length, right? But I could figure out, well actually, why don't we make this side x? And that way we have x on both sides. And that'll be easier to peg the third side because I know whatever this value is, let's call it y for a second. I know that y is going to be 100, right? That's the total number of feet I have, minus the length of the two sides. So that's going to be 100 minus 2x. Oh, and this is side y. The side of that is y as well. So I know that the area, which we can make as a function of x, is going to be x times y, right? It's a rectangle. Its area is x times y, or in other words, x times 100 minus 2x. There is my area function. Okay, so if I change x, I get a value of area. Area is the output. So now when I say the largest area, that means the highest point of my parabola. Okay, and now notice if I had taken my area function and distributed out the x, I would have ended up with negative 2x squared plus 100x. So this is a downward facing parabola. This parabola does something like this somewhere. And so the vertex is the highest point. Okay, so the point that we're looking for that will maximize the area is the vertex. Okay, great. Now, can we get it in vertex form? Well, in this case, for the sake of time, maybe we want to just do this formula here, the negative b over 2a. That'll give me my x, and then I can plug that in to get my y. Okay, so the x-coordinate of the vertex, again, is negative b over 2a. All right, so here a is negative 2, b is 100. So that's going to give me negative 100 over 2 times negative 2. That's negative 100 divided by negative 4 gives me 25. Okay, so that means the y-coordinate of my vertex, which is actually the area that I'm looking for, is going to be negative, let's see, maybe it's best to use the factored form here. So that's going to be 25 times 100 minus 2 times 25. Okay, so that's 25 times 100 minus 50 is 50, right? So that's going to be 1,250 square feet. All right, so the vertex has this form, 25, 1,250. And what this tells me now is that we can have a field of 1,250 square feet, right? And what are the dimensions of it? Well, we found x, right? The x of that vertex was 25. Okay, if we let one side be 25 feet and the other side, or the other length along the barn, that was my y, right? And what was y? 100 minus 2x. That's going to be 100 minus 2 times 25, which is 50 feet. All right, so if he makes a 25 by 50 feet field where the 50 feet's running parallel to the barn, that will be the maximum area he can have, and the maximum area he will have is 1,250 feet. Okay, so we have found the exact instance here. If I take this field and I let that be 50 and I let that be 25, that is the biggest field I will have with the amount of fence I have. And I hope this makes sense. Okay, so that's a run through of linear and quadratic functions. We are going to save common functions for next time. If you have any questions on this, please let me know. I'll be glad to help. I'll post these notes on Canvas, as well as a link to them in the description of this video. And I hope you guys are doing well. Let me know how I can help. Take care.